Hello everyone, I welcome you on my talk about hypervisor. The name is Consideration about Enabling Hypervisor in Open Source Firmware, namely coreboot. So my name is Piotr Król, I'm founder and embedded system consultant at 3MDEP, small Polish consulting company. I'm interested in open source firmware, or open source embedded firmware to be more precise, platform security and trusted computing. You can find me on various social media channels if you want to reach me. So what we will talk about today. First of all, I will introduce a little bit about hypervisor and virtualization technology. I would like to define some terminology. I will talk with you about embedded hypervisors and how they are different from known to everybody hypervisors used in cloud environment. Then I will introduce Bareflank, which is framework for scaffolding hypervisors written in C++. Then I will explain how we were able to include hypervisor as a payload in coreboot firmware. Then we will have demo and discuss what we can do further with our work. So what was the goal of that effort? First of all, we wanted to run a couple applications which will start in isolated virtual environment directly from SpyFlash. So obviously we had to have hypervisor inside Spy run directly from open source firmware. So why to do that? So first of all, to raise our experience with virtualization and hypervisors and understand better capabilities of hardware that we have, that we support, and of course to satisfy market demand where we see growth in demand for embedded hypervisors and use of hypervisors in, let's say, robotics, automotive, military applications. Okay, so a little bit about terminology. This is very scientific definition, but it is worth to think about it. So virtualization is the application of the layering principle through enforced modularity, whereby the exposed virtual resources is identical to underlying physical resource being virtualized. Yeah, this sounds very complicated, but if you think about that, layering, we can think about layering like abstraction with well-defined namespace. If we will think in practical way, let's say we have kind of big disk, and on top of that we create some layer, and above this layer we also see disk, but this disk, let's say, is just the piece of the real hardware which is below. And another capability of that layer is that we cannot get through that layer to access physical hardware. We just see what is exposed above that layer through this single abstraction, well-defined interface. And so the second capability is this enforced modularity, so the guarantee that the client of the layer cannot pass through that layer to access this abstracted resource. So okay, this still is kind of vague and sounds weird, but if we will think about, in real terms, if we will think, for example, about virtual memory, this is exactly what happened with page tables. Also, if we think about writes, our disk arrays, we have couple disks, but we expose that as some logical one disk. It depends on write, but one disk that has continuous space and is, for example, redundant. So that's kind of how virtualization works, and this is principle that can be applied not only in cloud environment, but in various other situations. So to move forward about definitions of the terminology, a virtual machine is an abstraction of complete compute environment. So we have this virtualization which is applied to whole compute environment, and then we can talk about virtual machine. hypervisor is a software that manages those virtual machines, and VMM is a portion of hypervisor that handle just CPU and memory virtualization. Typically, hypervisor also handle I/O or devices communication. So that's why hypervisor is wider term than virtual machine monitor. Okay, so hypervisors can be divided typically are divided in two groups, type 1 and type 2, but we define also type 0. It's mentioned in some papers, but it's not official naming. So we define type 0 hypervisor as a hypervisor which is built inside the firmware. So we have hardware, firmware is a part of hardware, and then in firmware we have hypervisor, and this hypervisor can start some OSs or some applications. Type 1 is a hypervisor which starts after firmware, and it's not part of the firmware. And then, for example, type 1 is Zen or Microsoft Hyper-V and others. And then we have type 2, which starts inside the operating system. This terminology has some gray areas. For example, Linux KVM and FreeBSD Beehive are like are part of OS. So we're thinking if this is really type 2 or type 1. So maybe this is type 1.5. So you know, like it's this whole types are kind of continuous and can have various features. Our hypervisor is type 0, and there are other type 0 hypervisors like IBM's LPARS or Oracle LDOMS, or we can use L4 kernel, call it L4RE, as a embedded hypervisor type 0. Okay, so what's behind embedded hypervisors and how they are different from regular hypervisors in cloud? So some of these features are common for both cloud used hypervisors and embedded hypervisors, but first of all, it's important to know that embedded hypervisors are quite new, and first use is noted around early 2000. When we compare that to, let's say, mainframe hypervisors, IBM mainframe hypervisors, it were invented, like, I don't know, in 60s or something. So this is big difference. So virtualization is very long on the market, but its use in embedded just rise over last 20 years. So those hypervisors are typically very efficient, are small and fast. So we cannot say like Zen is not exactly small, although it can be trimmed for some use cases, and there is some work, for example, for ARM, where they trimmed Zen like significantly for automotive use cases. Our hypervisors is relatively small, and I will tell you about that a little bit later. Hypervisor has minimal impact on system. To be honest, it just builds this layering and encapsulate some existing hardware, and do not provide like Zen a lot of support for various devices and tons of features. Embedded hypervisors are very narrowed, application-specific use cases. In case of security, it helps to minimize trusted computing base. So the trusted computing base is the piece of software or hardware or firmware which is critical to security of our system. And if this will be compromised, we are just doomed. Yeah. So this is a trusted computing base. And having small and efficient and reliable and the kind of testable hypervisor, embedded hypervisor, gives us ability to minimize this code base, which we call trusted computing base, which can cause, it will be compromised, it will cause huge problems for the system. It's easier to be certified and to get through reliability testing, and this is because it's small. Yeah. So if we talking about common criteria, the cost of certification depends on the amount of code that we have. It helps in subsystem encapsulation. This is also a capability of any hypervisor, but this one is focused on kind of giving minimal overhead to provide, let's say, some subsystem like crypto subsystem, the one VM, or let's say SATA controller to one VM, and so on and so on. So this is kind of very close to hardware encapsulation. Then in case of communication, big hypervisors have like very sophisticated methods and huge API for communication, but those embedded hypervisors typically use some implementation-specific communication, which rely on either processor instructions like VM call, VM func, or CPU ID, read write MSR, and so on, or EPT manipulation. So we can use those as a tools for building implementation-specific communication. And of course, depends how much information we want to exchange. We use those communication methods. And if we're talking about real-time capabilities, of course, if we have robotics or automotive, we want to have as little delay as possible. What means the overhead of the system and overhead of hypervisor have to be minimal. And in this case, this is the goal of the hypervisor, so it helps in improving real-time operation. And performance of those hypervisors is close to native because we have a little code that just do basic encapsulation, basic isolation. What about the applications? So typically mission and safety critical applications, as I mentioned. This is because we have strong isolation that relies on hardware. So we can, let's say, isolate critical and non-critical processes in separate VMs. And if non-critical process crash, then we can just, don't care if it not touch the hardware, not damage the platform, then we can continue operation with the critical process. If critical process fail, then we should have, of course, some handling procedure and correctly behave, do not cause any damage to human life, and so on and so on. Interesting use case is that typically with fault tolerant systems, we have fault detection application, and we want to control the operation of whole system. Let's say we have robotic arm, and in one VM we do some processing of arm movement, and in other we can verify if all the processing is correct, let's say by reversing computation or by testing various elements in the system. And if, let's say, something wrong happen in fault detection system, we can run some security procedures, some recovery from the fault. And in this case, we just can implement better, higher quality system. And this is normal practice in safety critical applications. Second feature is, and application is reuse of legacy code. Let's say we have a legacy code base, and which is very hard to extend, add the features, but the market demand additional features. So we take this legacy code, put that into VM, and then in other VM, and it is of course working in isolation, and in other VM we're putting some feature improvements, and hypervisor is kind of responsible for handling and coordinating who's accessing what and doing what, and in that way we can still keep the same hardware, and if the legacy system do not need all the resources, other resources can be consumed by new features. And of course, like kind of migration from uni-core systems to multi-core systems is simpler because we just scaling through virtual machines. Manageability is other feature of that we can easily add with embedded hypervisor, because if we have full control over hypervisor, then simply we can write a code that controls some behaviors of virtual machines and code that is inside virtual machines, and this gives us ability to, let's say, notify some management system and say, okay, all virtual machines are fine, working correctly, and or we can just give signal, okay, something's wrong, you have to investigate that system. Of course, also dynamic system updates will be will be easier. For example, Resin.io at some point presented. This was not with virtual machines. This was with containers, but the idea is very similar. So they had a flying drone, and they just switched the firmware when drone was in the air. So we can simply do similar thing, that was just switching processing to other VM, because we have full control over hypervisor. We can run other VM and just pass the control to other VM when with the newer software, which contain already updated software. So this is kind of something that we can implement with embedded hypervisors. So what we really did, this is overview of the architecture that we created. So most of you should be familiar with what CBFS is coreboot file system, which we keep inside SPI flash. And of course, it contains coreboot boot phases, which are boot block, ROM stage, RAM stage. And when the RAM stage finishes, typically jumps to payload. In this case, this is Bareflank payload. So like hypervisor scaffolded using Bareflank. I will explain Bareflank a little bit later. And then this is really hypervisor plus some additional code, which can start various VMs with, say, some arbitrary payload, for example, real-time operating system, and other with some, for example, general purpose OSs. Yeah, so this is a general overview of the design. What is Bareflank? So Bareflank is a lightweight hypervisor SDK written in C++. It contains support for all major platforms. Website do not mention that, but it also right now contains support for coreboot, or at least we described methods how to use already existing Bareflank generated hypervisor to be included in coreboot. It is led by Assured Information Security. It supports Intel, but structure of the project is prepared to support ARM and AMD, and they plan this support in future. Maybe even we will be interested in helping in AMD support. So most important features are support logic, which gives us memory management, like code that helps us with memory management, serial console printing, output, and this kind of stuff. So this is useful for debugging. Definitely embedded system serials are still used. So so nice to have that out of the box. And libc++, so standard library for C++. Also we have virtual CPU management, so vCPU management related to like a state of the virtual machine is there. Also virtual extension logic, virtualization extension logic, which is related to how to deal with CPU virtualization extension, how to use it, and in what order. So typically after scaffolding new hypervisor, so we have Bareflank is used to kind of scaffolding new hypervisor. So most work is related to implement handlers, like exit handlers, VM exit handlers, which, so VM exit happen when we call the communication methods that I mentioned before, like CPU ID, read MSR, VM call, VM func. So we just handling that to have some communication between hypervisors and VM, and in that way we can control the system through hypervisor. Okay, so business logic, any business logic, so this is kind of framework we can say, or SDK, and any business logic, if we want to implement with Bareflank, we have to do this as like a kind of separate code, as an extension of that, because Bareflank is not for and like for providing any business logic. So the idea for this hypervisor was introspection needs. So they run hypervisor, let's say in Windows. Nothing's happened. Like you run these hypervisors and like nothing's happened. The hypervisor is run. Everything just switching to virtual machine, and system just do not notice that. And then we can run, if we have correct handlers in hypervisor, we can run application inside operating system. And if this application calls some behaviors, then we have VM exit and can intercept that in hypervisor and, for example, I don't know, inspect memory or whatever we want to do to introspect what's going on in operating system. This is the purpose of this hypervisor. So project is a moving target, and this hit us many times. There are sometimes massive code changes and massive code drops, like in tens of thousands of lines. But if you work with it, it's a good idea to just freeze on some version and do not move, and this should work. And if there is no justification for updating the code, then you should not do that. Okay, so the instruction provided and support from community is very good. If like replies on GitHub coming very fast, there are videos that present how to use Bareflank, how to create your own hypervisor, and so we also when started had these problems about dependencies because Bareflank using very modern version of C++, so we need all the modern libraries, the newest CMake, and so on and so on. That cause some problems with stable distributions like Debian, also Ubuntu. So we created Docker, which contain all the dependencies, of course, for the version that we forked, because keeping up with the speed of development in Bareflank is quite hard. Yeah, also in the Bareflank Docker you can find instructions how to build UEFI hypervisor and how to test it, how to run it, and we use that output to build our hypervisor that we present here. The output of the process is VMMH, which contain bytecode of hypervisor, and I will talk a little bit about that later. Okay, so what's inside Bareflank payload, which I show you that runs after RAM stage? So there are two components, VMM, which is virtual machine monitor, and BF driver, Bareflank driver, and those components are, first is result of the Bareflank SDK build, which is kind of 88,000 lines of code, but this is just header with the bytecode. And if you look at it, it is around 1.2 meg. And this is without any customization. Yeah, so if we want to add some sophisticated VM exit handlers, then we have to also think that it will extend. Yeah, this size will grow. And we wrote BF driver, which is minimal C code, which provide necessary hypervisor hooks and code to launch VMM and then launch virtual machines also. It's around 6,000 lines of code. 1,000 was needed. 1,000 modification was needed in lib payload because we had to implement support for 64-bit architecture. And around 800 lines is for MP code, which is able to run code on given core. So I will explain why we need that later. So here you have kind of directory listing. We are in coreboot on Bareflank payload. This is our 4-core coreboot, 3MD 4-core coreboot, and you can just see what we have here. So common C is taken directly from Bareflank without modification. Include also contain bunch of headers which come directly from Bareflank. So that's why like most of the code is is coming from other project, and we wrote entry C, which can start VMM and payload. And there is also platform C, which contain code specific for memory handling. Okay, so this slide shows, like, I will not go like deep in the details. There is a research paper which was written by 3M Dev staff. So right now, a special kudos to Christian, Michał, and Łukasz for helping in writing this presentation, or mostly writing this presentation, this research paper. And this is graphics from the research paper, and it explains how this is. This is Bareflank payload, and this slide explains how initialization flow of Bareflank hypervisor going. So first of all, we have load VMM. So we want to load this environment in which we will. So we want to load the virtual machine monitor, which will help us run virtual machines. Yeah. Then. So there is Bareflank init, which we can do some stuff here, but right now there is nothing. We configure a memory for VMM, then we initialize it. We do some hardware-related instructions, so this is Intel-specific here. And finally, we can launch virtual machines on host CPU, so which is BSP, and other CPUs, which are application processors, if we have multiple cores. So this is basically it. So you can see that this phase start VMM is on each core. So, and then we can continue with, let's say, running operating systems in VMs that will be existing then on various cores. Okay, if we like thinking about hypervisor as a coreboot payload, typically type 2 hypervisors use some OS-specific API to just hand over control to just run VM OS in VM, or we can also, so Bareflank also support UEFI boot services to do that, but because we are in coreboot, we need something more, and because of that we had to extend lib payload, and we added 64-bit support to it. We added exception handling, but we didn't exercise drivers too much, and there may be still some problems with various lib payload drivers. So contribution welcome. So there were some size problems, or either can be size problems in some cases. So definitely we need something in VM that will start operating system, or of course we can use some bare metal RTOS. Then this is not valid requirement. But we wanted to start some general purpose operating system, so we choose SeaBIOS, and we included also in the flash, and of course this caused that we have less space, and to be honest, we needed continuous SPI space to put our hypervisor there. So uncompressed, it was like 3.5 meg. After compression, we have 310 kilobytes. Okay, so what kind of problems we faced? One problem that appeared during development was that when we, so most of you should know that coreboot expose memory map in so-called coreboot table. So this is like a coreboot deliverable for operating system, let's say, and or for further phase of booting, for payloads, for bootloader. So we have this coreboot table, which kind of define how memory map is laid out. But what then happened is that we run our Bareflank payload, which links with the lib payload, and because lib payload allocations kind of are not related with coreboot table, and lib payload assume that the memory it allocates will just be not needed after the payload will exit, then it not modify coreboot table despite changing memory map and using some areas in memory. For example, in this situation, this lib payload have to allocate memory for virtual machine monitor that I showed you on previous slide. Yeah? So it allocates this memory and then runs VM. And if in the VM we have SeaBIOS, which kind of would like to use coreboot tables to see what memory I can use and where I can write and what I can do with that, but those tables are not modified by lib payload, and VMM can be in area that SeaBIOS don't know that cannot use. And yeah, and if it tries to use it, it will simply crash because we will destroy virtual machine monitor code. Yeah? So because of that, we have to reserve that memory that will be used for VMM right here when we're filling coreboot tables. And this is what we did, and but we kind of had to realize that this is a problem, and this took some time. There is also some game like switching between 32 bits, 64 bits, and then get back to 32 bits. Because coreboot is 32, Bareflank is 64, and then SeaBIOS is 32. Yeah, so we have to kind of switch modes on x86, which is kind of game, and not maybe not the trivial one, and especially when you have some problems in lib payload, where, for example, there are assumptions like this. What means in if we will have 60, if we will be in 64-bit, this is not true, and yeah, so this is the place where those kind of problems were detected, and we fixed that, but of course still debugging and understanding why we have this crash was needed. Also, we changed order of entries in global descriptor table because it didn't match already changed its structure in coreboot. So it looks like synchronizing coreboot and lib payload has kind of problems, and I don't know, like this have to be probably addressed by the maintainers, and someone have to keep an eye if we're changing something like that. We should reflect that also in lib payload. Last problem that we had, or problem, or kind of something that we have to think about, is that we have to run VMX instruction on all cores, because if we will not, if we will have one core which do not have monitor running, then the problem is it can access its C whole memory and can access. And to be honest, like this is like those are processes, but there should be kind of reserved memory here for virtual machine monitor. And of course, if this core has unrestricted access to whole memory, it can corrupt either memory of the VMs or VMM hypervisor itself, which will result in system crash, which we don't want. Yeah. So because of that, we running VMX instruction on each core, and this gives us also some cool additional features. For example, we can better manage access, VM access to hardware, because since we have hypervisor which intercepts access to hardware, we can say, okay, this machine needs less access, that machine needs more access to hardware, so we can kind of prioritize and help them to, let's say, have well-performing access to the physical layer. Okay, I told you that. So yeah, again, lib payload to the rescue, and we had to implement code that can run VMX on each core and say, okay, please run on this core, run VMX. Yeah. So because like there is no way to just do that like in instruction set. Yeah. So we have to run code on each core to enable that. Or even each core or thread, because if we have hyper-threading, then we have logical processors which also need this operation. Okay, EPT and memory reservation. So I would say, like, I'm not memory management expert. EPT is even more complex than regular page tables, or it's extension of page tables that keeping everything in your head without drawing would be very hard. So please do not ask complicated questions about that. But we had some considerations about that, and And we thought that if it is possible to avoid this memory reservation, and this pre-filling of coreboot tables with some reserved memory. And in general, yes, it is possible, but then we have to go into rabbit hole and implement and generate and update extended page tables at runtime. And then we have to also add some memory management functions, so we can allocate pages and deallocate pages for VMs. And this sounds to be very complicated, and more to that, it also gives some overhead. Of course, it will bloat the hypervisor, and this will cause that we just are not so close native performance as we would like to be. And in our opinion, this approach is not exactly good for embedded hypervisor that we wanted to build, especially if we plan to run real-time operating systems in virtual machines. So one of the last graphics that I have here is explains this game, like switching from 32-bit to 64-bit and get back to 32-bit. And yeah, so when we jump to, after RAM stage from coreboot, when we jump to Bareflank payload, which is kind of created from two components that I mentioned, a BF driver and VMM, what we do is of course, BF driver is linked with lib payload, which gives us this ability of transitioning to 64-bit, which we need here. It has this memory management, so it can allocate memory for virtual machine monitor, and it has the CBF functions that helps to get code of VMM from the SPI and can load payload. Yeah, so that's why we need lib payload. Then, as I explained, we have these three phases, which first is loading VMM, starting VMM on each core, and then we can start payload on given core. So on given core, so inside given virtual machine, we can say, and yeah, and we are done because we have populated our embedded systems with VMs that we need. And maybe I didn't mention that, but embedded systems have like a fixed set of virtual machines typically, so we have like we don't change that over lifetime of embedded system with hypervisor application. Okay, so demo time, and what we would like to improve in future. So first of all, we would like to integrate Bareflank build system with coreboot, since right now there is kind of game that we need. We have to run scaffolding. We're getting this VMMH, which we have to move manually to coreboot build system, and then we can run build, which includes the VMM. Then there is no way with our current implementation to have some flexibility about hardware partitioning. So to divide let's say, okay, you have access to SATA controller, you have access to Ethernet controller, and so on and so on. We don't have that capability right now, and we would like to have that because various customers may have various needs, and various configurations of embedded hypervisor may be needed. Then there is this problem with memory management and memory map. This definitely should be improved. We're thinking about how to solve those issues, and definitely we should update Bareflank codebase since the beginning of 2019 it changed a little bit, and as I said, we would like to contribute or support AMD SVM feature of or capability of Bareflank, and this is mostly what we have in mind right now, and of course we are open for suggestion, and that's all. Thank you very much.